This is another case of stability analysis where we are given a process by a transfer function k over 10s plus 1, 5s plus 1. And it's given that a controller is designed for this process using the direct synthesis method with tau CL equals 5. Now it asks you if this controller is designed for k equals 1 and then gain changes to one plus alpha. Okay, so it asks you for up to what value of alpha the process, meaning the closed loop process, will remain stable. Okay, that's the problem to solve here. Now see that for this case, the controller, so using the direct synthesis method, so we'll get the controller to be a PID controller with this Kc to be 1 over k and tau 1 plus tau 2 over tau CL. I'll get the value to be 3. This 10 plus 5, 15 over 5 and 1 over 1, that give you 3. And tau I will get to be tau 1 plus tau 2, this 15, and tau D to be tau 1 tau 2 over tau 1 plus tau 2, that gives a value 50 over 50. I'm keeping it 50 over 50 in this way for some reason. So you get the controller to be 3 times 1 plus 1 over tau is, so 15s, plus tau ds, so 50 over 15s. Okay, that's the controller. Now you implement the controller in the process and the process changes. Okay, now we have to find the characteristic equation for this changed process. So if we look at the characteristic equation, we get 1 plus Gp Gc equals 0. So we'll have 1 plus Gp is given by this. However, do remember that now k changed to 1 plus alpha and the denominator remains the same. And Gc is our controller, so it's 3 times 1 plus 1 over 15s plus 50 over 15s. Okay. So setting this to be 0, it gives the characteristic equation. Now if we look at this characteristic equation, we'll have, by simplification, if we multiply the entire term by 10s plus 1 plus 5s plus 1 times 15s, so we'll have 15s times 10s plus 1 times 5s plus 1 plus we'll have 1 plus alpha times 3 times you have here in this case if you multiply everything by 15s we'll have 15s plus 1 plus 50s squared equals 0. Okay. Now before further multiplying all of this, you need to just multiply this to give 15s times this will be simply 15s plus 1 plus 50s squared. I am writing it this way just to having matching with this one plus 1 plus alpha times 3 15s plus 1 plus 50s squared equals 0. So we are trying to find the value of alpha for which this will remain stable. Okay. Now you see this term is common to both. So we'll have this 15s plus 1 plus alpha should be 0. Now do remember that the other part becomes irrelevant for this case simply because for that one has already 2 poles which will be negative, so that part is stable anyway. We need to figure out that for this part that contains the alpha, for which value of alpha it will remain stable. So now if we say that find the root for this case, we'll have s will become negative 1 plus alpha over 5. Okay. So for stability what we need to have, that 5 is already a positive number. So to have this to be negative, we'll have to have 1 plus alpha should be positive, or alpha should be greater than negative 1. Okay. So it shows that this is the value of alpha. This is the recurrent on alpha for which the process will remain stable. So that's what we are asked to find in the first place, that find the value of alpha for which the process will remain stable. So this is just another example where you can use the stability criteria to analyze when a process changes up to what point the closed loop system will remain stable.